So let us get started with some of the quick revisions of fundamentals. And in this video, we are going to talk about determinants and traces, and we will try to add some geometric interpretation to determinants. Now, determinants is definitely one of the most important concepts when it comes to linear algebra, and a determinant is a mathematical object that we often use in while calculating the inverse or while solving the equations or system of equations. Now, when we talk about determinants, we can also always think determinant of any matrix A as some transformation that takes a matrix of size m cross n into a real number. So we will represent the characteristics of entire matrix by just one number. And of course, as you can imagine, two matrices which look very different from each other, they still can have the same value of determinant, and hence that determinant is not unique for two different matrices. How to calculate the determinant? So basically, when we talk about a 2 cross 2 matrix, let us say A11, A12, A21, A22, we simply say that in this case, determinant is A11, A22 minus A12, A21. Now, when we go to more bigger matrices, so if we are talking about a 3 cross 3 matrix, let us say A11, A12, A2, A and A13, A21, A22, A23, A31, A32, A33. Now, we can always write this as A11 times A22, A33 minus A32, A23 minus A12, then masking these two would be A21, A33 minus A23, A31 plus A13 times. So basically taking the determinant around that, and this would be the submatrix that we would be dealing with, A21, A32 minus A22, A31. And when we solve this particular expression, we are going to get an output as a real number if all the values within a particular matrix are all real. Hence, this is a simple way we can calculate this determinant in the context of matrices. Now, by the way, whatever we were writing here or whatever we were scribbling here, this has got a special name, what we call as the Laplace expansion. So Laplace expansion is basically says that the determinant of any matrix A can be written as summation of k equal to 1 to n, and when we are expanding along the rows, along the columns, as we did in this case, we are going from one column to another and so on, and we were expanding it, so it becomes minus 1 raised to power k plus j. That's why you see that there is one negative sign here and two positive sign here, because we are adding up the jk, the indices of the particular element around which we are expanding, and this would be akj, that is the element or the row element about which we will take the smaller determinant, which in this case we were taking the determinant of 2 cross 2 matrices, so that would be determinant of smaller matrix or submatrix, which we qualify as determinant kj. And this dangerously looking Laplace expansion is nothing but the usual way we have learned how to expand particular matrices. Now the question arises, what is the importance of these matrices? What these two matrices guarantee? So let's begin with some of the very simple results that you have heard very often, that is testing the invertibility, whether we can calculate the inverse or not. When we were talking about reduced row echelon form, we talked about the inverse, and also inverse mapping can be seen as that if we have any matrix B, which if multiplied by A, and the result is an identity matrix, and of course in this case A is a square matrix, B is also a square matrix, and identity matrix by definition is also a square matrix. So if this identity holds true, we would say that B is inverse of A, and typically B is represented by A inverse. Now A inverse can be calculated as, for again let us stick to our two-dimensional matrix or 2 cross 2 matrix, where we say this is A11, A22, A12 and A21. we say that A inverse is given as A11 A22 minus A12 A21, and here these two elements will change their position becoming A22 A11, and off diagonal elements will change their sign becoming minus A12 and minus A21. And we can clearly see that this inverse is only defined if A11 A22 minus A12 A21 is not equal to 0. And this we just learned that this is also the determinant of the matrix A, which is determinant of 2 cross 2 matrix, and this has not to be equal to 0 for matrix to be invertible. As long as it is equal to 0, the inverse is not defined, and that is what this determinant tells us, that whether a given square matrix would be having its inverse or not. Also, when we talk about ranks, we learned that ranks represent the number of independent columns or rows in given matrix. So if we have dependent row, that would mean that essentially we can reduce one entire column to 0, 0, 0 by taking care of that dependencies. And hence, if we are talking about a square matrix of size n, if it is not a full ranked matrix, that is R is less than n, that would mean one of the rows or one of the columns can be expressed as zeros. And if that can be the case, and if we take the expansion using the Laplace expansion that we just spoke about the column or about the row which is expressed as 0, we can clearly see that inverse is not defined, or full ranked matrix are the only invertible matrix. So only matrix that has full rank, they are invertible. Otherwise, if there is not a full rank matrix, it is not invertible. Secondly, we also learned about the concept of trace. So a quick revision: trace is the sum of elements along the diagonal. And how this trace is related to determinant, let us see. Now, we might have heard of the term called as upper or lower triangular matrix. Now, upper and lower triangular matrix are commonly used whenever we have to do some matrix decomposition. And one of the common decomposition which makes use of upper and lower triangular matrices is Cholesky decomposition. We'll not go into detail of Cholesky decomposition in this video, but in subsequent videos we'll talk about that what is its significance, how positive definite matrices can be decomposed using Cholesky decomposition. But in case of upper and lower triangular matrix, we say that if all the elements below diagonal are equal to 0, we are essentially talking about upper triangular matrix. It is a triangular because imagine that we have a matrix with all zeros here, and here we can identify a triangle where there's nothing, everything is null here, and there are some values stored here. So these are non-zero components, these are all zeros. Hence we say that since numbers exist only in upper part, this becomes upper triangular matrix. And from this we can also derive the definition of lower triangular matrix. If we say that all zeros are in top part, non-zeros are in bottom part, that becomes the lower triangular matrix. Now, the convenience these upper and lower triangular matrix offer is in terms of calculation of determinant. So for example, if a matrix A is expressed in its upper triangular form, then the determinant of that triangular matrix is simply the product of all the elements along the diagonal, right? So we learned about the trace, which is summation. So we can also define the product of diagonal in form of the determinant. So these are the two fundamental concepts that all of us should be familiar of whenever we are dealing with the matrices.